Good morning, good evening for those who are still jet-lagged. I'm Edouard Alligand, and this is Joel Falcou. We are the author of the Brigand library. Today we're going to spend 1 hour to explain to you what you can do with the Brigand library and why we designed it, where it comes from. There's going to be 2 practical examples of what you can do with it, and this is examples taking from thank you very much. Coming from actually both of our production code. We started the work like something like 1 year ago. The reason why I started working on this is because on the production code we were a massive user of Boost MPL, which is Boost Metaprogramming library. And we were getting more and more annoyed with the compilation time of Boost MPL and the fact that it's been done in C++03. If you leverage the novelties of the C++11 language, there is a possibility to write much more efficient metaprogramming code. And I have been reading an article written by Peter Dimhoff, which was, I think, inspired from something done by Eric Niebler. And I realized that it would be relatively easy to write a metaprogramming library. And Joel joined me right after because he was working almost on exactly the same thing on his own end. The source code is available on GitHub, and it's the Boost software license, so there is really no constraint on how you can use it. The question that comes very often is, why should I care about metaprogramming library? What should I care about metaprogramming? Isn't metaprogramming something which is extremely advanced C++? Do I really need it? And we hope that at the end of the hour you will think that it's actually useful. Even if it were 100% useless, it's a very, very, very good mental exercise, and it will make you a better programmer, I believe. So this talk will start, then we're going to explain the principle of Brigand, what you have inside the library, how it works. Then we're going to show you 2 use cases, and then it will be time for questions.
Thank you. So let's see what's inside Brigand. So as Edo says, Brigand is actually based on the general principle of Boost MPL, which means that we reuse a bunch of their concepts. So as MPL, what we do is you don't want to handle metaprogramming components in the wild by writing random template functions and random template classes. You need to have some kind of structure. And the structure we took is basically the Boost MPL1, which rely on this separation between compile-time algorithms working on compile-time sequence using compile-time functions. So we have this subset of algorithms and functions that is displayed there, where we have a very, limited but useful list of sequence. So Boost MPL is known to have stuff like compile-time vector, compile-time list, compile-time hash maps, compile-time set, and so on. And in fact, the only ones that actually make sense are those 3, which is the list, the set, and the map. The difference between list and vector are completely, unconfidential. So we get rid of that. So you usually start a Brigand code by fitting something in the sequence, on which you can apply some algorithms like finding types in the sequence, counting how many times something is happening in the sequence, transforming it, sort, merging it, and so on and so on and so on. And you can use pre-built function to build your computation on the types. And one of the most fancy stuff we have in Brigand is the as something functions that can actually help you turn a sequence of something into another kind of sequence, or ending up with, okay, I finished compiling something in a sequence of types, and now I want a tuple of that, or I want a variant of that, and so on and so on. So we have easy way to go back into, let's say, the non-compile time code. so the question is, what is actually a sequence in terms of metaprogramming? And what is the core element of that? So in Boost MPL, a sequence was something that has a definite tag that was fitting some interface that the Boost MPL function were able to recognize. What we do is throw that everywhere away, and a type list in Brigand is any type which has a variadic parameters of types. So Brigand list is a list because it's something which is of the form Brigand list t ... And so is std tuple, so is std variant and whatnot. So is std vector, for example, which contains two types, the types and the allocator type. So as long as your type is a template type with a list of something, it's a valid compile time list. And this actually makes a lot of things very simpler to manipulate. So we don't need anymore to have a special MPL adapter that takes some types and turn it into a sequence. Everything that looks like this is a sequence. As a small detail, we also have way to properly handle strange types like void or C-style array, and we don't care about what's inside the type list. So as long as you have a template class with variadic template list, you're set, you have a compile time Brigand list. So what do we do on that? Well, you can do the usual operation on this, like adding a type, popping a type, finding something, concatenating two lists. The other simplification with respect to MPL is that the fact everything is eager, so you don't need to do type name something something dot type. You just apply the meta function on the list and you get another list directly. So everything works like it's written on the can. So you add a char on list 1, you can pop the front of list 2, and you can append both lists and done. And the very interesting part of most compile time libraries is the fact you can actually run algorithm like transform on a list of types, applying an arbitrary so-called meta function or meta function class, which is something that say I'm taking a type as a parameters and I'm returning you a type with some transformation. So for example, if you want to go from this list of charbol int into something which is the same list but with pointer everywhere, you can just say, okay, transform this list, and for every type in the list, just add a pointer to the current type. So this is also something we take a page from MPL by using this kind of placeholders that looks like lambda placeholders. Can also have stuff like find and another set of functions that work like this. So find will give you a way to look for a type in a sequence, or for a type that actually fulfill a given condition. The way Boost MPL was ending this was having a concept of meta compile time iterator, which was rather complex. So what we do is actually use a range-based approach. So when you find something in a list, what it does, it consumes a type in the list until it finds something, and it will return you the list which is so that the first element in the list is one type you were looking for, and you have the rest of the list at your disposal, which means that if you want to, well, look for the second one, you can pop from this type and find again on the remaining of the list. And sometimes what you want to do is not to find something. You don't care where is it. What you want to know is it inside. So we have a found function that say, basically, did I find something in my list that was fulfilling some value, and you get a bool that tell you yes or no. And finally, same way that MPL was doing this, we need a bunch of bridges to go back from the compile time to the runtime world. So we have a for each function that takes parameters, which is a compile time type list, and you can pass an arbitrary lambda function or functors that takes a Brigand type of t as a parameters. And you can do whatever you want with this t inside, like, I don't know, printing its name, instantiating it, calling a function on it, and so on. The reason we do this with this type wrapper is basically because we want to be able to have lists that contain void or other non-instantiable types. So this is a small price to pay to get something which is more homogeneous in terms of the way we actually handle those types. So now it's time for our first use case. Edouard?
Okay, thank you. I'm going to give you some context about the use case. So in my company, we sell a database. It's a client server. And so the client and the server exchange messages. And what we want to do is to see what are we going to break the protocol in a new version. What happens if we add a new message? And we would like to do that with the minimum amount of effort possible every time we do something. And the idea is to use template metaprogramming to do compile time introspection and generation and see if the sequence of bytes matches the structure we have and if the structure we have matches the sequence of bytes. And if we look at the whole work that we have to do, of course, not everything can be solved with Brigand, because you can imagine there is a serialization, there is a type introspection. We use a boost fusion for that. But Brigand is going to help us in those two stages. And we're going to see that it actually is absolutely not stratospheric code. It's very, very, very easy. And I hope you will agree with me. So the first thing you do is you have your messages, and every message is a structure. This is the way the code is organized. And what's very interesting is that the messages don't have to have any relation between each other, meaning that you don't need to have inheritance, you don't have to do any kind of polymorphism. You can have two structures that share absolutely nothing and still use this technique. So personally, from an algebraic point of view, I think it's very powerful. But the only thing you have to do is to somehow have a list of all these messages somewhere. And this list is a list of types. So what we're going to use is going to use a Brigand list, but we could imagine a program where you would have, let's say, a variant, because let's say your message is a variant, and then you would not even have to do this step, which is we put all the command in a list. In the code we put in different lists for the kind of message we have, and then we concatene all the lists into one big list that we're going to use to do the processing. You have a lot of flexibility in the way you can do this. You can also use the push back, push front, whatever function you want. The next step is that you may want to clean up the list. Imagine you have some messages that you are going to deprecate and that you know that you don't really want to test for backward or forward compatibility anymore. The technique we use is to have a type which is deprecated and which is going to signal that this message is going to be deprecated very soon. And we're going to use that in an algorithm to remove them from the list just after that. We also use an ID to have a unique message identifier. This is something we do in our case. It's a very efficient technique in metaprogramming to have a unique ID for every message, and we're going to see at the end what you can do with this. So how do we remove a deprecated message? Again, the goal is to write as little code as possible. In Boost now, you have something called type, I think it's TTI is for Boost type introspection library, I think. So you don't have to write anymore all the sFine code or any trick. You just do, please generate for me a meta function which is going to be named as type deprecated for me. And what we do is we use the remove if algorithm on our list, use the function provided, and not unlike std_bind, we say we use the Brigand placeholder and we get the list without the deprecated flag. And it would work for any flag. Let's say you have a message that works on a specific platform and you just want to test every platform one by one, you could use this technique. Then let's say you want to sort the messages by ID. You could also want to sort them by size. Again, we're going to use the Brigand algorithm, which is sort. And the only trick we're going to do is to write this little function to say, by the way, we want to look at the ID member of every message, and we want to use that as a criteria to do the sorting. And then we used quote to basically say to sort, hey, by the way, this is the functor you're going to use for sorting. This is extremely straightforward. Of course, here you can imagine that you have the whole list of messages. And once we... was too far away. And once we had that, then we got in the meat of the thing. It's when we bridge compile time code with runtime code. So the Brigand library helped us to do all the compile time code to inspect every time, make sure we don't forget any type. There is no room for typos or I forget a message. You are 100% certain that every message you're going to get in your functor is going to be the message you want to test. And here, all you have to do is to, once you have your type, you won. Then you just can create, instantiate the type. You can call your serialization code. Or let's imagine all you want to do is to generate a documentation. You could also here just print the list if that's what you want. This is just an idea that I want to give you. Then your imagination can find many other applications, I'm sure. Let's not go too far. So as a homework, you can say, let's detect at compile time that I don't have duplicate IDs. This is something you can try. I can give you a hint. You just need to use the proper structure. It's something like 2 lines of Brigand, I think. And this means that when your code compiles, you know you don't have duplicate IDs. And if you wrote one time in your life a client-server application, you know that duplicate IDs in messages can be a very nasty bug. This way, at compilation time, you know that at least this is correct. And the earlier you find a bug, the less expensive it is.
Question?
Yes. Do you have like a counter which could count up the IDs at compile time?
So the question is, do we have something to count the IDs at compile time?
You mean to increment? No, we don't have it in Brigand. To do it, it's funny because I've been asked exactly the same question by someone else. I think it would be not very hard to do it within a single CPP file. The problem is if you wanted to do it across different CPP files. This is much harder, but in our case, all the messages are in the headers. So you could imagine that you have a CPP file which is reference and that creates the new ID at every time it's instantiated. You could create a list of integers, for example, and you would add a new version every time you call it.
Or you can actually use a set maybe.
Yeah.
So you can actually count and detect duplicates at the same time.
Yeah, actually this is the answer to the...
Oops.
No, it doesn't matter, but yes, you could use, in Brigand we have different structures and including maps and sets. So I think with a set it's not too difficult to solve this problem. And actually we could even add something in Brigand to do it for you. What do you think?
You write the code.
So my partner in crime agrees.
The second question I would have, your test generator, will the tests fail at compile time or at runtime?
The question is, does the test generator fail at compile time or runtime?
That's a very good question, and I failed to explain that at the beginning. The generator creates a program which then you run and it's going to generate the code with the tests. And in our case, it's boost test code. But at compile time, you don't do everything because in our case, we have compile time serialization code, etc. But taking a structure with the member initialized, serialize that in the bytes of array, you can only do it at runtime. So
using TMP to generate test cases for the runtime.
Exactly. So the remark was we use template metaprogramming to generate the test code, which is then going to be incorporated in the continuous integration, and this is exactly what we do. No other question?
Okay, so let's go on to the second use case, which comes from a completely different type of application. So at Namescale, we deal with high-performance computing tools, and one of the stuff you learn quickly when you do this is that your data processing code is only as fast as it's cache friendly, because basically right now, what limits a computer processing speed is more the memory speed than anything else. So if you want to take care of actually using the most of your hardware, you need to be cache friendly. You can find publication in the wild that say basically if you don't take care of your cache, you're basically wasting 90% of your CPU power. So you don't want to do that. And one way to actually be able to manage to get out of these bugs kind of things is to manage the data layout of your computation, so you know that whatever you do, you're okay with your cache. One way to do this is stemming from techniques to handle arrays of structure. The traditional object-oriented way wants us to have stuff like vector of some objects that represent your data or your state, and whenever you want to do computation on that, you just run over your vector or structure and do something. And in some cases, it's okay, but sometimes that's not what you want to do, because you may want to process data. For example, we have this array of structures, so array is a square bracket, the structure is a squarely one. Let's say you want to do something like, I want to do the sum of all the member M1 and divide every M2 by this sum. If you do the sum of every M1 with this layout, you will end up wasting half of your cache story M2 you don't care about. So you may want to have a data layout which is more like a structure of array, where you end up with structures that contain an array for each members. So you end up with value of all the member 1 and then value of all the member 2. And in fact, the correct way to do this is a third way, which is called the array of structure of array, which is basically this used as a structure into that, where you will statically limit the size and repeat it by blocks, block size having the good idea to be a multiple of the cache size and so on. So you may want to test one or the other, because sometimes the application you write wants this, and sometimes you want that, sometimes you want the third one, and you doesn't know. So we wanted to have a way to say, this is a structure, this is how the data is laid out at the abstraction level, and give me this kind of data layout, please. So what we did was, taking a structure or a tuple, we built the proper representation. And after that, what we did was building allocators, iterators, range that can iterate over the structure we just built, whatever the actual layout. And so what we did was actually using Brigand with Boost Fusion to automate the first part, which is actually rebuilding the data structure we use inside. So let's say we have a small structure, which is a float and 3 integers, for example. So we use Boost Fusion that abstract to say, okay, this structure that contains these 4 members, wave X, Y, Z, is actually a fusion sequence. So fusion sequences are made so you can actually at compile time access an element of a structure the same way you access an element of a tuple, by playing with the fact that the tuple and the structure are basically the same, except one has member with name and the other does not. So once we have that, you could actually use Boost Fusion on any instance of my data to extract the first, second, third, or fourth element of the data structure. Okay, so that was quite easy. Now, what do we win with that? Well, Boost Fusion gives us a meta function and a function which is called asVector that takes an arbitrary fusion sequence and flatten it into a Boost Fusion vector, which happens to be interesting when you end up computing complex type with fusions and you want to go to something more simple. And in our case, if you pass a fusion adapted struct to asVector, well, you end up with that. So what it is? Well, it's a type, it's a template type with a variadic number of type parameters. So this thing is directly a Brigand list. So it doesn't have to do anything. So we turn our arbitrary fusion sequence into a vector which happens to be compatible with Brigand. And now what we do is that we can actually butcher it the way we want. So let's say we have this ASOA structure that takes something of the form container of something and then some options. So it can work with list, vector, whatever, and take care of all the other stuff. So what we do is we take the type T, we turn it into a Brigand list by calling asBrigand. So either you have something like a tuple already, or something else, and then it gets flattened, and we extract the vector from the inside. And what we just do is, what we want to do is going from a container of T to a list of container of each member of T, which happens to be what we do with transform, that run over the list of members base, and put it inside this template parameters container, and put all the other options afterwards, okay? You could have something more complicated that look what's inside there and replace whatever T it found with the base type and so on. For most standard container, it doesn't matter, because if it's an allocator, it will get rebind inside and so on and so on. And once we have that, so if we pass, for example, my data, we end up with a list which is a vector of float int, int, int. It gets turned into a Brigand list of vector of float, vector of int, vector of int, vector of int. But we can do nothing with that because I cannot instantiate a Brigand list. So what we do is we turn it into a tuple, and the SOA, the two SOA aliases just give you the tuple of vector or container of whatever you were looking at. So you pass a vector of structure and you end up with a tuple of vector of each members of the structure. And then you can actually instantiate that and you get your data layout already done in the correct way. So having the data layout done is half of the jokes. And the question is, how would you write that, which is something that say, I have a container of something and I want something which is an iterator that can iterate in a, structured way on every subpart of the data layout. So the idea is to do the exact same thing and trying to find a way to fit that into a zip iterator that will zip over every part of the data layout. So as in terms of performances, we show that whenever the SOA representation is the correct one, you can have basically a speed up around 2 or 3 depending on the complexity of the members. You have cases where just not loading data from the third and fourth member because you don't care of it win you that much space in the cache, and you can tremendously improve the performances. So that's a small tool we have that's actually very useful. And the fact that you just have to turn it on and off by calling it or not on the vector of your structures, you can quickly test if it makes sense to go to this kind of data layout, or if you can stuck with the simple one. So there's a lot of other stuff we can do with that. That's the beginning of the idea. People are working on having what we call hybrid data layout, where part of the data structure is in an array of structure and part of it is still a structure of array. So you can actually choose which members of the structure you can group by in the cache or not. So it was actually probably just missing probably a couple of lines, but everything with Brigand was turned into this. The old equivalent MPL and Boost Fusion code was 3 times as big, so it was a real win. So let's conclude now.
Thank you. So we have time then to have a look at how the code looks, because the example, they are very short. The conclusion we have is that since C++11 and even more with C++14, writing template metaprogramming is much easier. It's much easier for 2 reasons. First, in the language, we have features that makes especially variadic templates everything more straightforward. You don't have to use macros to generate a lot of classes just to have a list of types. You even have built in the language now the tuple, which is a very, very powerful tool in template metaprogramming, because it's a candidate for a type of a list of types. The other thing is with C++11 and C++14, compilation time for template metaprogramming is much shorter. The most frequent comment I heard about template metaprogramming is, okay, sure, it's useful, but before my code took like a couple of seconds to compile, and now it takes like 2 days. And with Brigand, we have instant compile time. And if it takes a lot of time, it's your fault, it's not our fault.
And if I wanted to actually be more mean than that, it's actually instant compile time, including on that compiler.
We just did you. Yes, and the code we wrote works on Visual Studio 2013. You need the latest update, but it works, and it's in the tests. And last but not least, I think it's actually useful. It's not just something like you could say, okay, I did some clever tricks and look at how much a good programmer I am, and no one understands my code. No, it's very useful. In my case and in the case of Joel, the results is that it took less time to achieve the results. The code is more reliable, and you have the feedback about the correctness of your actions at compile time, which is as soon as it's humanly possible, because sooner than that would be in your head, but that never happens. Then, yes, I think the goal is to make your job easier. We are very open to comments and suggestions, as always. We're already about to release version 1.3. In our case, the library has been in production for 6 months, 9 months?
At least.
And in your case?
Probably 6 to 8 months too.
And we know that other people also use them in their code. Now we have time for questions, and we're going to have a look at the layout. Yes.
Just so
I think it's a good idea, yes.
Okay, except not.
Except it doesn't work.
Doesn't work. The other button, of course. Was I saying? So yeah. So we have our GitHub there. So just if you want to get to the website, the other stuff I wanted to speak about is the fact that someone is actually playing around with, trying to find who is actually having the fastest metaprogramming library. So Luis Dion is maintaining this MetaBench web page that compare a bunch of metaprogramming libraries on different types of algorithm and stuff. So now, which one is the one we should show and not the other one? You remember? I'm just actually just picking one at random. So yeah, so Metal is another metaprogramming library from, I don't remember his name, from some other guy. So yeah, so the funny thing is to look at the x-axis, in fact, which is the number of types in the type list. Okay, so all it's okay, but I wanted to find one with MPL actually. Yeah, so MPL blows up at 50 or 100 something, and all the modern metaprogramming library can go up to I don't know how many types. I think Odin has a use case with 2,000 types or something like that.
Yeah.
At some point.
It works.
And it works.
There's something interesting to say about Boost MPL is that you have to define specific macros if you want to have something like more than 20 types in a list. So 20 types in a list of types can sound like a lot, but actually it's not that much. It's very easy if you do tricks like we've shown, like I want to have all my messages in a list. 20 messages is nothing.
Yeah, and to go on this, in the old version of Boost CMD, we were using MPL. At some point, we need to have this tree of types that describe shuffling of vectors, and it was blowing up after 20. Except for some cases, you have like 300,000, so it doesn't work well. So that's, for example, timing for transforms, where we see again that, well, MPL just blow up at some point, and the modern take on writing these metaprogramming libraries, can you actually go far better? Well, we also happen to be the fastest on this one, just saying, but well. So okay, so this is also a very good
I think there's a question.
resources. There is a question? So the question is benchmarking stuff up to 500 something types is realistic? Well, the fact is we actually have people with these exact use cases where you wanted to build a 1,000 types list and sort it and find the first one that fits something before generating a piece of code. I don't remember the exact domain, but it was related to electronics device or whatever. where he wanted everything to be computed at compile time as much as it can, so he can, have the tightest binary possible. So we actually had people that play with 30 to 5. Okay. Now, the one criticism that Eric did on that, which was actually an actual something question, which was, should we benchmark stuff like I have a list of 5,000 types all the same, or 5,000 types all different? Because depending on the algorithms, memorization inside the compiler can kick in or not, and so on and so on. That's an open problem. No brand. Well, yeah, well.
If you have the same type over and over.
Yeah, if you have the same type over and over, actually what happens is that the compiler remembers that he sees a type, so he doesn't have to mangle it again or whatever it does for fetching it inside the compile time section. Now, well, I think that testing over different types is what happens regularly. So maybe the correct way to handle that could be you have to say, you fix the size of your template list, like, I don't know, like 200, and you play with, let's say, the density of types. So you can go from 0%, every type are the same, up to 50%, every type are repeated up to twice, and so on and so on. So you can actually have a decent look at what's going on. Benchmarking compile time algorithm, I think the MetaBench is the first kind of effort like this, which is actually standardized and formalized. So maybe there is Crank and Nikki to cook around, but well, it's the first one. Another question?
I noticed that you have selected Clang 3.8. Is there a difference like to GCC or other compilers?
So is there any difference between Clang and the other one? I don't know. We can actually check what happens on other one. Well, yeah, a bit. Okay, you didn't do your homework, Edouard.
It's a GCC 6.
Yeah, GCC 6.
Doesn't count.
Yeah, yeah, you see, but
You see, now.
yeah, we are speaking like tenths of a second anyway of compile time. So, but if you look at MPL, you see that it goes quite up. It changed a bit because I think the algorithm inside the compilers to handle the types may be different. I don't know how Clang handles the variadics, but I know it's different from GCC, so probably that's the reason. Yeah, it changed, but the worst case we handled was this 50-something type list on Visual Studio, and it just compiled like a normal code, so job's done. But yeah, compiler's version actually is important, yeah.
There's two remarks I think are important. The question is, 500 types are useless is not up to us to decide. We just provide the facilities, and there is no reason to decide in advance that people should not do it. If someone comes up with a valid use case, you just give the possibility to people to use as many types as they want. Also, one merit of this benchmark is that all libraries improved by realizing that they had, for example, a quadratic behavior in some algorithms. And at the beginning, in Brigand, we have a technique we call the fast lane, and everybody in the beginning was saying, yeah, it's a useless technique, we won't do it, and we were much faster than anyone else. And with time,
everybody does it now, so.
No, so it's good. It's the purpose. Of course, the benchmark will only tell that you're good at the benchmark. It will not see the real.
Yeah, the other funny stuff is that at some point we decided to change the way we represent lambda function. Because it was clear that was something that was pulling us upwards some other techniques. So I think it's the same emulation between all of those. Between Meta by Eric, MPL, and the metal guys. So, well.
And also, so yes, the goal is that ideally the cost for the library should be 0. That it's not because you want to use a technique that is going to have a huge impact on your code. And when it becomes 0, then people are going to use it more and more. And I think it will result in better code in the end. Maybe we can have a look at different benchmarks.
Yeah.
Okay.
So, it's clear that modern day TMP libraries are kicking the butt of MPL because of new features in the standard. The process of migrating from MPL to Brigand or HANA or whatever, what is that like?
So the question is, okay, so you have modern template metaprogramming libraries. They are better in a way than BoostMPL. Just to be sure, BoostMPL was the huge source of inspiration, and it's a very, very good foundation. We just take the logic and port it to a new language in a way. And the question is, fine, I have my Boost MPL program and I want to port it to another library. How long is it going to take? I think it's very quick because especially in Brigand, you have almost a one-to-one match on the name. So find works differently. You say goodbye to iterators, but this is something you will thank us for it because it's much more convenient.
The other change is the fact that we are all eager.
Yes.
Don't have any more lazy.
We have lazy, but it's in different
it's
namespace.
explicit. Yeah.
And you don't have to switch everything at the same time. You can have the two to cohabit for a while.
I just noticed that this seems to be Louis' webpage, but I don't see HANA in the list.
Aha, because so the question is where is Anna in this list? So that's because we are dealing with pure type operation. So I think if you go to this,
Maybe sort.
yeah, then you get okay. Thank you, Louis, to just blow my stuff, and I think you were okay. I need that, of course.
Maybe.
Yeah, I need a proper compiler to get Anna to compile. So yeah, so you find Anna benchmark into the heterogeneous tabs. So he separated the one that deals with types only and the one that deals with heterogeneous operations. So you get the comparison against fusion and stuff like this and tuple there, while the other one is basically all compile time type manipulation because it's completely different piece to benchmarks.
And actually, Anna and Brigand are very complementary from one another. They don't really solve exactly the same problem, which from the outside sounds a bit crazy. Like, what? I need 2 template metaprogramming libraries? And the answer is no, 2 is not enough.
You need all of them.
Yes.
Okay, thank you again.
So we can have a look at the code organization to answer the question of, okay, fine. So you showed us examples. So I have my wizard of
Keyboard master.
keyboard master, because the keyboard is actually too big for my hands. So I can't press 2 keys at the same time. So if we look at this, you will, if you are a Boost MPL guy, which is for me what I've spent most of my time with, you will find yourself in a place where the organization looks a little bit the same. And to give credits where due for the documentation, we just imitated whatever was the Boost MPL documentation and copied the same structure. You will find the algorithms here. The names are very explicit. And we have actually documentation and tutorials that we wrote to get you started. Like to answer the very simple question of how do I create type lists? How do I use algorithms? And you will find it on the home page. And as for the documentation organization, you will find again everything on the home page. So I'm ready for more questions. Yes.
I can just go away. So I don't really use the Microsoft compiler. Have they implemented expressions FINE yet? Because that's
No.
okay. So what is the process like of getting your TMP library to compile on the Microsoft compiler?
So the question is, did Microsoft implement?
So the question is, what kind of black magic voodoo stuff did we did to compile on Visual Studio? That's all right. So actually, the expression FINE is not that of the big deal we had to fight against because we don't use much.
No, we don't use it at all.
We tried at some point, but we found out it's not that useful for what we. Oh no, wait. We use it at some point. I'm saying stupid stuff.
And we
use for set. Set use FINE, but it's the small corner of expression FINE that Visual Studio is happy with. So that was quite lucky. No, the main issue with Visual Studio was sometimes you doesn't know why you're writing your template aliases because you need them, and at some point you end up with having something like using type equal alias 1 of alias 2 of something of alias 3. and the compiler gets confused for whatever reasons. And then if you do, okay, using result 1 is alias 1 of this, and result 2 is alias 2 of result 1, and so on. So you just, piecewise enumerate the steps, then it compiles. And sometimes for completely different alias of different complexity, you don't really know why. So whenever we hit that, we just slice the computation.
I think you should disable some of.
Yeah, I think I should have. Yeah, whatever.
The trick is.
Yeah, we need to decompose some of the computation of types because Visual Studio get cranky at some point. But it was mainly that. I don't think we had any other big problem.
We crashed every compiler that exists, for sure.
That's part of my job description anyway.
But the IC in Visual Studio the most frequent, it's because of the tokenizer, which is like a ring buffer of 3 elements, I think.
Do they have?
No.
Do they have a tokenizer?
Most of the time, when you get a crash in Visual Studio, you create an intermediate type, and then you get around the crash. So you just have sometimes, if you look at the source code of Brigand, you're going to say, why do they have an intermediate type? Then you have the explanation, and we have actually very, very few if-defs for the compilers.
So just for going back on this Sphinx stuff, so that's part of the set implementation. So what set is you have a set of types that must be unique. So what we do is we take every types, put it into a box, and we inherit for every box of every type in the set list of types. And the box contains a small interface, small interface for answering questions like contains, get key, and whatever, which is just, okay, for given types T and K, if you contains K, or if only if you are actually able to, if you are inheriting from the max set of everything. If you does not inherit from that, that means it would not contain in the set. And same for ASCII and same for erase, that just removes the type if and only if it's found into the list of object inheritance. And this decal type usage is okay for Visual Studio. And so you ended up with basically building this type over and over again until you consume all the type into the set.
We can also maybe show what the fast lane technique is and
yes.
why it's faster.
What's the fast lane?
So the question is, what's a fast lane technique? So let's say you have transform, for example. Is transform fast lane actually?
I think everything is.
Yeah, okay. So let's say you have transform. So you have transform of T ... and you say just build up, find the file meanwhile. You do the stuff with ... But ... has a cost. So what we say is that if it's empty, you return the empty list. If you have one single type, you apply the meta function to the single type once. If you have 2 types, you do it twice, and so on, up to, let's say, 16. And when you have more than 16 types, what you do is you compute the 16 first with the fastlane one, and you pass the rest to the transform, which means that basically if you have n types in your type list, you only need at most n divided by 16 templates instantiation.
So how did you pick 16?
Because more than 16, I was bored actually copy-pasting the code, so I said, 16 is enough, or maybe even 8 is enough, or something. Yeah, which one is that?
It's transform, but there's been some other hacks.
What's the L is this name? Oh yeah, Rot 98.
Okay. There is some other black magic, but the goal is that
You're unrolling variadic templates.
Yeah.
Yes, that's what we do.
Basically, we enroll variadic templates.
We transform.
That's fun.
There's been a blog series about this just by Odin Holmes.
Yes, he's a contributor.
And he's the one who wrote all this, actually. So.
The first version of Brigand, we had very simple enrolling, and he pushed the technique even further.
And Odin came, and some place I don't even recognize the code anyway, but Odin has been working with us for quite a long time now. He's quite a very interesting contributor to have around. So Odin's technique is basically what we use. Or let's say Odin's technique has been probably polished on Brigand before he makes his blog post or whatever, but it's basically what he's doing. I think at is on roll also with the funky stuff. or is it? Yeah.
Yes, actually it's the map which
yes, the map.
forced us to do this. When we had a discussion, because basically Brigand was designed on the phone, we had a conversation and we were like, okay, so we have the list, it's easy. Now then we reached the map, but you really want to have logarithmic complexity for the lookup of the map. And we wanted to run on Visual Studio, which elided all the advanced techniques we could use on Clang. So I don't remember who said, but then
Probably me.
actually I think it's me, but I wanted to be polite. You just need two French people to disagree.
I'm not sure about that, but yes.
Even when I'm alone, I think I can disagree with myself. I think it's sequences.
Fitting sequence.
Yes. Yes, it's actually the basic is to say, and you have a specific technique.
It's ASCII or something. No?
Yes, at key. It's going to be in map, no?
Yes. Oh. There.
Here, map.
Yeah.
So yes, so for the map, you really want to have the lookup to be very fast. And some of this is, some intermediate type is because of, and so the idea is here. Oh, no, not anymore. Because
ASCII. I said it's in ASCII.
ASCII? Where? Ah, yes. Sorry.
Okay, except not.
No, the
Well,
thing
it's
is,
somewhere.
we simplified everything.
No, I think I can find that. Pretend to say something interesting meanwhile.
Okay. So, yes. I think it's Jonathan who came up with a different idea from Fastlane, but if you go back in the history, you will see that you can use this technique. Any other question? No question? So we'll wait for Joel to find the code.
Would you like us to clap?
Yeah.
Okay.
Yeah. Okay, thank you.